Welcome to Organic Chemistry 1, Chapter 2, Assignments. Okay, the first problem, you need to predict the hybridization geometry, and approximate bond angles for atoms other than hydrogen. So the first thing you have to do is draw your correct Lewis structure. So the first one, A, would be CH3, CH, double bond, another hydrogen, and then CH3. So this is a correct Lewis bond structure, and make sure everything has 4 bonds for carbon. Now, the hybridization here, since this carbon has 4 things connected to it, that would be an sp3. And the way I always remember this is the S has 1 there, and then the P is 3, and you add those subscripts together, and there's 4. So there'd be 4 things. Go to this the geometry, so that's hybridization. The geometry for an sp3 is 109.5 degrees. It's a tetrahedral. And you'll get used to these because they're all pretty much the same. Okay, so carbon here, there's only a few choices. This carbon, the blue carbon, has 1, 2, 3. So that's an sp2. So you can add your superscripts together. 1 plus 2 is 3. And sp2 is flat, and it's planar. So it's like the plane, flat as a piece of paper. And those are 120 degree bond angles. And it's flat planar is the geometry. Okay, let's go to the next one. We'll make this one black. This one has 1, 2, 3. So it's also sp2. Same, flat planar, 120 degrees. And then this one is 4 things, 1, 2, 3, 4. So that's sp3, 109.5 degrees, tetrahedral. Okay, going on to B, you have to draw your correct Lewis bond structure. This is a condensed formula. That carbon has 3 hydrogens. The next one has 1 hydrogen, and it's double bonded to the nitrogen. Nitrogen has 3 bonds there with a lone pair. Okay, so that's your Lewis bond structure. Hydrogen has 1 bond, carbon has 4. Now this carbon here, once again, is connected to 4 things, so that's going to be sp3, 109 degrees, 0.5 in tetrahedral. The next carbon, 1, 2, 3, so that's sp2, that's flat, planar, and 120 degrees. And then the nitrogen you have to include the lone pair as like a leg or a thing because it's going to take up an orbital space. So that's 1, 2, 3, so that's sp2. Nitrogen's sp2. And nitrogen sp2 then would be flat and planar. And you'll see whenever you have a double bond, so you have multiple bonds, you're going to have either sp2 or sp3. Okay, C, carbon dioxide. When you draw this Lewis bond structure, you should get this looking molecule here. And the oxygen then takes up 1, 2, 3. So that's oxygen is going to be sp2. Both of them are sp2. And that's going to be planar and 120 degrees. The carbon has 1, 2. So it's sp. Okay, so if you add those superscripts together, that's just 2 things. That's sp for the carbon. And that's going to be linear. And linear is 180 degrees. So yes, it's 180. Because remember, full circle is 360. Okay, the next compound, D, would be CH2. So let's put 2 hydrogens on that carbon. Then the next carbon has an oxygen. Oxygen likes 2 bonds with 2 lone pairs, and that gives 1, 2, 3, 4 there. So 1, 2, 3, 4. So let's look. This carbon here then has 1, 2, 3 things. So it's sp2. sp2. Remember, that's planar and 120 degrees. This carbon here has 1, 2. So that's sp. It's going to be linear, 180 degrees. And then the oxygen here has 1, 2 lone pairs, and then 3. So it's going to be sp2. Once again, that's planar and 120 degrees. Okay, going over to E, HCN. So if you go ahead and draw the linear structure here, hydrogen has 1 bond, carbon likes 4 bonds with no lone pairs, nitrogen likes 3 bonds with 1 lone pair, so that's Lewis structure. This carbon here has 2 things bonded to it, and so that's going to be sp, that's going to be linear, that's going to be 180 degrees. Nitrogen has 1, 2, so it's also sp. Okay, so the next one, CH3. Go ahead and write the CH3, and then oxygen, and then another CH3. Positive charge. I don't see where that would have a positive charge, so just omit that positive charge. Yeah, so something went wrong there, but let's just go ahead and make it without a positive charge. This carbon and this carbon are both going to be an sp3. As you can see, 1, 2, 3, 4 things. And the oxygen has 1, 2, 3, 4, so it's also an sp3. sp3 are always tetrahedral, and they're 109.5 degrees. It's actually less than because it's not all the same thing connected to it. Okay, G is the hydronium. The hydronium, so that's oxygen with 3 bonds. If you do the formal charge, you'll see that the oxygen has a positive charge. And then, so oxygen here will be 1, 2, 3, and then lone pairs, 4 things. So that's sp3. That's tetrahedral and less than 109.5 degrees. H is trimethylamine. So you have CH3 connected to the central nitrogen. And nitrogen has 3 bonds with 1 lone pair. Each carbon here has 1, 2, 3, 4 things. So each carbon is an sp3, tetrahedral, 109.5 degrees. And the nitrogen here has 1, 2, 3, and then the lone pair, 4 things. So it is also an sp3, tetrahedral, less than 109.5 degrees. Okay, let's do I. I is CH2O. So the 2 hydrogens are on the carbon, and then the carbon is connected to the oxygen. Oxygen likes 2 bonds, 2 lone pairs. That gives carbon the 4. This is actually called formaldehyde. Preserves bodies, right? Chemical used for preserved bodies. Okay, so let's count the carbon. We have 1, 2, 3 things. So this carbon is going to be sp2, because you add the superscripts together, sp2, and that is always 120 degree bond angles, and it's going to be planar. So it's flat, like a piece of paper. The oxygen has 1, 2, 3 things, so it's also sp2 and planar. And then we have J. J is methanol. So that alcohol looks like this with the 2 lone pairs. This carbon has 1, 2, 3, 4 things, so it's sp3. And this oxygen has 1, 2, 3, 4. It's also sp3. sp3 is tetrahedral less than 109.5 degrees. Okay, assignment 2.1, problem 2. Now we're going to draw the orbital pictures of the pi bonding in the following compounds. So once again, you got to be able to draw these Lewis bond structures. And then this carbon is connected to another carbon, which is connected to an oxygen, which is connected to a carbon with 3 hydrogens. Carbon likes 4 bonds, no lone pairs. Oxygen likes 2 bonds with 2 lone pairs. And when you're dealing with pi bonds, so each one of these is a sigma bond. I'm going to put the red, this is sigma bond. These are your single bonds. So if you had to count how many sigma bonds hold the nuclei together, the different atoms. So you have 1, 2, 3, 4, 5, 6, 7, 8, 9. You have 9 sigma bonds. We are trying to draw orbital pictures of the pi bonds. Pi bonding is always going to be unhybridized p orbitals. So if you remember, you have a p of x, a p of y, and a p of z in the atomic orbitals, and they look like dumbbell shapes. Dumbbell shapes. And then, of course, you have the x orientation, the y orientation, the z orientation. Well, one of these have been used up for hybridization, okay? So this one's used up, the x, because it's had to be hybridized with the s orbital to make your sigma bond. That leaves you in pi bonding, you have, if it's just a multiple bond, like a double bond, it leaves you with 1 unhybridized p orbital. And if it's a triple bond, you have to use 2. You have to do the x and the y. So basically you're looking at this multiple bond right here, and what happens is parallel in a different direction, you have those electrons here, okay? So they're either in the y plane or the z plane, and they overlap, and that's how they overlap. Okay, so let's now go on to the next one, CH3. And then you have carbon connected to another carbon, and then it's connected to CHO. So you put the hydrogen on that carbon. Oxygen likes 2 bonds with 2 lone pairs. And this carbon has 4 bonds. This carbon has 2, so it needs another 2 bonds. So it's 3, 4, 3, 4. Okay, so now our sigma bonds here would be 1, 2, 3, 4, 5, 6, 7, 8. So this molecule has 8 sigma bonds. And those are going to be the hybridized. So here for carbon, the first carbon is sp3. The second carbon is going to be an sp with an sp. And then the next one's going to be an sp overlap with an sp2. But this one's orbital pictures. So we have pi bond here. So we're going to have unhybridized p orbitals for this first one here. And then for the other multiple bond, we would put it here. So you could shade these together if you wanted. And then this one has an overlap for this pi bond for carbon. So those would be the orbitals. Okay, now we're going on to the next one. Our Lewis bond structure, CH2, double bond to another carbon, CH. Now we're on the next one, CH, with a double bond to a CH, and a CH3. We're going to make sure we have carbon has the octet of 4 bonds for each one of these. 4, 1, 2, 3, 3, 4, 1, 2, 3, 4. Yes, so it looks good. If you want to do the hybridization here, you'd say this is an sp2 because this carbon is connected to 3 things. This is 1, 2, 3. This is an sp2 carbon. 1, 2. This is an sp2 carbon. This is an sp2 carbon, and this is an sp3 carbon. So this carbon is connected to 4 things. Now, our number of sigma bonds are the single bonds, and they connect covalently to each of the nuclei. So if you had to count your sigma bonds, you count 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. I counted 12 sigma bonds. And this problem wants pictures of the pi orbitals. So here we have, we can just put them in this plane if we want. So you have this carbon and then this carbon here, and their unhybridized p orbital. Electrons are overlapping there, and that would be our pi bonds, our orbitals. This problem is on assignment 2.2, problem 1. Which of the following compounds shows cis-trans isomerism? Draw the cis and trans isomer, the ones that do. Okay, so CH3, CH, CH, CH3. So the way you look at this is you look at the 2 carbons bonded by double bonds, and you say, you look at the first carbon, carbon number 1, you look at the 2 things connected, because there's only going to be 2 things connected because it's already double bonded to the carbon. And then you say, is CH3 and hydrogen different? And you say yes. So then you go to the next carbon, and then you say, okay, is CH3 and hydrogen different? Yes. So if both are different on each of the carbons, the doubly bonded, then it shows, then yes, you have cis-trans isomerism. So here, you look at who's higher molecular weight, CH3 or hydrogen. Well, that has a molecular weight of 1, that has a molecular weight of 15, 12, 13, 14, 15. Okay, so here we got 15 molecular weight and 1. So the 15 and 1 are on the higher side, and the 15, now both 15 are the higher side, so this is going to be your cis. So if you want to draw your trans, just put one of them on the opposite side, and now your higher molecular weight are on opposite sides, and that would be your trans. Okay, go to the next one. CH3. This is an alkyne, CH3. This is linear. No, so alkyne, the triple bond, no isomerization. So no isomerism. Okay, the next compound. So you look at your first carbon and you say, are these 2 different? Hydrogen is the same as a hydrogen, so there's going to be no cis-trans isomerization. So no isomerism. So that's a no. This is no, that's no, this is yes. You don't even have to look at the next one. Cyclopentene. Cyclopentene is this structure here. You're going to have to start learning how to name your hydrocarbons. They're in the last section of this chapter. And in theory, you could have cis-trans isomerism, but in theory, there's no, because you can't have you'll learn that you cannot have no trans carbon-carbon double bond until you get 8 carbons in a ring. So you have to get up, this only has 5 carbons in a ring. Your ring has to get up to 8 carbons, so it has to be cyclooctene in order to be able to have a trans carbon-carbon double bond. So I would say no. Theoretically, yes, but the answer is no here. Okay, the next compound, let's draw this one out. CH3, CH, double bond carbons over here. This has a CH2, CH3 connected to this carbon, and then we have it connected to this CH2, CH2, CH3. And so you look at the first carbon, you say, is CH3 and hydrogen different? Yes, they're different. Then you look at the next carbon of the carbon-carbon double bond, and you say, okay, 2 carbons, that's an ethyl, and this is 3 carbons, that's a propyl. Propyl is different than ethyl, so yes. And now the way we drew this is this cis or trans. Well, between the methyl and the hydrogen, the methyl has the higher molecular weight, and then between the ethyl, which would be 24, about 29, versus the propyl, of course, 3 times 12 is 36, so about 40 or something like that. So 40 is greater than 39, so these are between this methyl group and this propyl, they're on opposite sides, so that would be trans. And then if you were to draw the cis, you would just draw carbon double bond, and you put the methyl on the top, and then you would put the propyl on the top and the ethyl on the bottom. And that would be your cis, because the higher molecular weight is on the same side. Okay, and then our next compound here, CH3, CH, double bond nitrogen, CH3, and then we have the double bond here. So this is kind of a tricky one. And so you just look at this carbon, there's 2 different groups, so that's a yes. Methyl is different than hydrogen. And then on the nitrogen, you have a lone pair, and then you have a methyl, and they're different, so you would say yes. And this would be trans, because the higher molecular weight would be 15 and 15, and they're on opposite sides. And this would then, of course, be cis. Okay, assignment 2.2, problem 2, predict the hybridization and geometry of the carbon and nitrogen atoms in the following ions. So we're going to have to draw resonance structures. So go ahead and draw each one of these out. This is a carbonyl, and you can count the number of electrons here for your total valence electrons. Carbon has, there's 3 carbons, and each carbon has 4, so that's 12. Oxygen, we have 1, and it contributes to 6 valence electrons because it's in group 6. Hydrogen, you have 5 times 1, so that's 5. And then you have a negative charge, so you're going to have to add 1 there. So when you add this up, you have 18 valence electrons. You can count them now. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24. So 24 valence electrons. So what did I do wrong? 5 is 5. 3 carbons is 12. And 1 is 6. Okay, so obviously I added this up wrong. So 12 plus 12 is 24. Okay, so we've accounted for our valence electrons, and this is our structure. Now the electrons that are non-bonding or in a pi orbital can move to make a resonance structure. So we're showing the movement of electrons. We're showing our resonance arrow. This is how you draw the resonance structures. All the atoms remain in the same place. And when you redo your formal charges, you'll see that oxygen now no longer has 2 bonds and 2 lone pairs. It has 3 and 1 bond, 3 non-bonding and 1 bonding bond, so that makes it a negative charge. The negative charge is conserved, so these are your resonance structures. And it says the hybridization geometry of the carbon atoms in the following. So this carbon is sp3, the first one, and it stays sp3. The carbonyl carbon, the blue carbon here, has 1, 2, 3, so it's sp2. And over here it has 1, 2, 3, so it stays sp2. And then the last carbon here, we'll make it black, has 1, 2, 3, and because it can, that lone pair can, is next to an sp2, it's actually considered an sp2 carbon. And this is sp2. sp2 are 120 degrees, and it's planar. The sp3 would be less than 109.5 degrees and tetrahedral. These electrons, in order to do resonance structures, have to be sp2 or sp. Okay, you have to have unhybridized p orbitals in order to do pi bonding, alkyne binding, and to move between the non-bonding pairs, to go from atom to atom. It's almost kind of like an electrical wire. Okay, so the next compound here, so let's draw this. Nitrogen has 2 hydrogens, and then it's connected. This would be a carbon here. So that carbon is double bonded to the next carbon. And then you have the next one, CH2, CH, and you can just go ahead and put a positive charge on that, this nitrogen. And what's not shown here is 1, 2, 3, that's a hydrogen, 1, 2, 3, that's a hydrogen. So you can just go ahead and put a hydrogen in there and a hydrogen on that carbon. Now, for the hybridization, we have a pi bond here, okay? And so 1, 2, 3, that's going to be an sp2. This carbon is also an sp2. This carbon, 1, 2, 3, 4, this is an sp3. 1, 2, 3, 4. Okay, so that's sp3, has less than 109.5 degrees, and it's tetrahedral. Okay, so these electrons in this pi bond cannot migrate to this carbon here. This carbon is an sp2. So that vacant orbital has an unhybridized p orbital, that's sp2. Now this nitrogen, because it's next to an sp2, is considered an sp2, because those electrons can go to that carbon, and then these can go here. And then that makes a resonance structure, hence my resonance arrow. Put your nitrogen, carbon, carbon, lone pairs there. Every atom stays bonded the same. So there's your hydrogen. There's your hydrogen on your carbon. There's your hydrogen. Now you have your negative charge. You have a negative charge? You'd have to have a negative charge. CHH. And there's your plus. 1, 2, 3, 4, 5, 6, 7, 8. Oh, and there's your positive charge. There you go. So I have to make sure it's maintained. So you see the original molecule has an overall charge of plus. So the new resonance structure also has to have an overall molecule charge of plus. So this plus and minus formal charges cancel each other out. You know the first one is your major contributor because you don't have so much charge. Here you have a lot more charge, less number of bonds. Actually, it might be the same number of bonds. Now, this is going to stay the same. So this is still sp2. This is sp2. This is sp2. This is sp3. And this is sp2. But you cannot go those electrons can go from this nitrogen through this carbon, but it can't go through this carbon because this is like a roadblock because this is an sp3. The geometry would not allow those electrons because what's happening is if you have an unhybridized p orbital, you have in the same plane these unhybridized p orbitals, and those electrons can just go back and forth and travel. So actually a resonance structure is a hybrid. It's really all the same. That's how we draw it on paper. Okay, we have one more, and this is a nitrile. So we have nitrogen triple bonded to that carbon, and then that carbon is bonded to CH2. And you have, when you see that charge, then that's a lone pair on carbon for its formal charge. Okay, so when we look at this, this is an sp, this nitrogen. This carbon is an sp because it's only bonded to two things. 1, 2, that's sp if you add those superscripts together. And then this is 1, this is actually going to be an sp2 because you have a lone pair next to an atom that has multiple bonds. Okay, because if it can, it will. So what happens is these electrons on this carbon will go to this carbon, and then those electrons will go to nitrogen. And then what that looks like is lone pairs go on that nitrogen carbon, and then this makes a double bond here. And so let's make sure these electrons here are now here. These electrons here are now here. And we've got to make sure our formal charge are correct because you can see this carbon's okay. This carbon has 4 bonds. It's okay. But this one now has the negative charge on the nitrogen because there's 2 bonds and 2 lone pairs. Now this is sp, 1, 2, 3 things. sp2, I'm sorry, yeah. This is sp, there's 2 things. And then this is sp2. Once again, because there's an unhybridized p orbital, those electrons can travel and overlap through these orbitals. Problem 2. Assignment 2.2, problem 3, give the relationship between the following pairs of structures. Okay, you can either have same, cis-trans isomers. They can be constitutional, meaning they're structural isomers. They're not isomers, they're different molecular formula. So the first thing you want to do here is make sure you got the same formula. 1, 2, 3, 4. So that's C4, 3, 4, 5, 6, 7, 8. H8. Here we have 1, 2, 3, 4. C4, 3, 4, 5, 6, 7, 8. So they're definitely the same molecular formula. And is the double bond the same? 1, 2, 3, 4. It's on the carbon 2. 1, 2, 3, 4. Yes, it's on carbon 2. So this means, if you look at it even more closely, these methyl groups are on the same side. These methyl groups are on the opposite side. So this would be cis-trans isomers. Okay, let's go to the next one. This is C4H8, the same as this compound here. This is 1, 2, 3, 4, C4, 3, 4, 1, 2, 3, 4. Okay, so that's 6, 7, 8, 8. So they have the same molecular formula, but if you look, the double bond is on carbon number 2 here. And the double bond here is on number 2. But this, if you name this, it would be 2-butene. This, your longest chain, is a 3 carbon. So it would be, oh, you'd have to keep it in there. You have to include the double bond. So it would be 1, 2, 3. That's your longest chain. So it would be 1, actually it'd be 2-methyl. This is your substituent, 2-methyl dash 1-propene. So it has a totally different name, okay? So these would be constitutional. So these are constitutional or structural isomers. So they have the same molecular formula, but different connectivity. And you can always tell the different connectivity if you learn how to name compounds. Here, 1, 2, 3, 4, 5, 6, 7, C7. Here we have 1, 2, 3, 4, 5, 6, 7, C7. And then we have 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. 14 hydrogens. 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. Okay, 14 hydrogens. And so now look at the connectivity. You've got to include the longest chain given the double bond, the lowest number. So 1, 2, 3, 1, 2, 3. So we'll start from left to right. 1, 2, 3, 4, 5, 6. So this name of this compound would be 3-methyl-3-hexene. And then this compound here would be 1, 2, 3, 4, 5, 6. So this one here would be 3-methyl 3-hexene. And then we've got to see if we have cis and trans. So this is, you look at this carbon first. It has a hydrogen and an ethyl. This has a methyl and an ethyl. So the ethyl are on the opposite sides. So this would be E. That's trans. And then this compound here, had between the methyl and the ethyl's on that side, and the ethyl or the hydrogen. So this would be cis, which is Z. So they are cis-trans isomers. Okay, looking at this compound here, that's cis. Calling your hydrogens, you'll see that this is trans. So these are also cis-trans isomers. You can count them and do the molecular weight. And if you do the molecular weight, you'll see that you have C10, C10. Okay, this compound here, we have the same molecular formula if you do that, but you can see you don't even have to worry about, even though they are cis and trans, the connectivity is different. So here, if you go count from this carbon, 1, and then you have to go through the double bond to give the lowest count, 2, 3. So it's 1 with your alkene starting at carbon number 2. This one here, call that 1, 2, 3, is 1 with your carbonyl, but your alkene is on number 3. So the connectivity is different in these. So these would once again be structural isomers or constitutional. Okay, this compound here, the molecular formula should be the same. 1, 2, 3. Hydrogen, 1, 2, 3, 4, 5. And a chlorine. Same is going to happen here. C3, H3, 4, 5. And chlorine. So they have the same. But your chlorine on this one, so if you counted 1, 2, 3, it's this would be 3-chloro. You don't have to name the one, but you could do 1-propene because there's 3 carbons. There's your double bond, ene, alkene. And here you'd start with 1, 2, 3. And so this one would be 1-chloro, 1-propene. So this is different connectivity. So these would be, once again, structural or constitutional isomers. Okay, we're on the last problem assignment, 2.3. Problem 1. For each of the following compounds, draw the Lewis structure. show how the bond dipole moment and those of any non-bonding pairs of electrons contribute to the molecular dipole. Predict whether the compound will have a large, small, or zero dipole moment. Okay, for your quizzes and exams, you can either predict that it has large or zero, or you could just say a dipole moment, okay? So either it has a dipole moment, because you're not going to know the magnitude. But basically, looking at the electronegativity differences as you go up a column and you go to the left, you increase electronegativity. So you can see that there is a difference between the carbon and nitrogen electronegativity. Lone pairs are always going to have a delta negative. And so we're going to look at this. So when you get the heteroatoms, go ahead and put in your lone pair. And the carbons are going to be delta positive, and the electrons are definitely delta negative. So the way you would normally do this, you could see that it's kind of going to go from the carbon, push those electrons towards the nitrogen, and then nitrogen with its lone pair, this is going to be your net dipole. And then you can say that and you can do that with the micro is greater than 1D. You can just do that. Okay, this compound here is acetonitrile, so you need to go ahead and draw out the full Lewis bond structure here. And between carbon and nitrogen, it's going to go towards the nitrogen. Nitrogen has a lone pair, so this is going to be your net. And your dipole is greater than 1D. I think it's like a 3.96. A lot of your solvents, that's going to be a large dipole. Okay, carbon tetrabromide. So it's going to look like this. And what's going to happen, you can put the lone pairs on your bromine. And if you look at the electronegativity difference between bromine, it's going to go, and carbon, it's going to go towards the bromine. But because this has symmetry, each one of these are going to pull equally in the opposite direction, the symmetry. So the dipole is going to be 0. Okay, this compound here is acetone. You use that in the lab. It is a solvent. So this is a ketone. And between the carbon and oxygen, each one of these are going to push towards the carbon oxygen. So your overall net dipole is going to look like this. And you can just do greater than 1D. I think that's like a 2.86. Okay, acetonitrile. Here's your nitrile again. Each one of these look like this triple bonded nitrogen here. But do you see how you have symmetry here? Because you have symmetry, each one of these are going to pull towards that nitrogen, right? But it's going to cancel out just like the carbon tetrabromide, so your overall dipole moment is going to be 0. This compound here, you're going to have your lone pairs on your nitrogen. All the carbon, everything's going to do a net dipole towards that nitrogen. And so you're going to say that this has greater than 0, dipole greater than 0. Here, the chlorine has its lone pairs between the carbon, so everything's going to go towards the chlorine for the overall. And you can say the the dipole moment is greater than 0. Now, the reason why the dipoles are important because they determine the properties. So you can do solubilities, and properties are your solubilities, boiling points, different ways these molecules interact with other materials and each other. So this ether here looks like this, and that's diethyl ether, and this is butanol. So we've talked about in class how water has only a molecular weight of 18, but it has a boiling point of greater than 100 degrees. Now you get something like methane gas has a molecular weight of 16, and it has a boiling point that's less than 0 degrees Celsius. Okay, so the difference between this is that water can do hydrogen bonding. Hydrogen bonding requirement, you have to have an oxygen, nitrogen, or fluorine. Can't be any other of those than those. And you have to have plus a hydrogen. Can't have hydrogen bond without a hydrogen. So you either have one of these three plus a hydrogen. Now, if it's solubility in water, then it's how does it react with water? Well, water has a hydrogen. So as long as you have an oxygen or a nitrogen or fluorine, you can hydrogen bond with water. But when you're dealing with boiling points here, boiling points, there's no water around. So it's how does it interact with each other? And so the two things you're asking, can this hydrogen bond with itself? And the answer is no. Okay, there's no hydrogen bond. There's no hydrogen to hydrogen bond. Can it hydrogen bond with water? And the answer is yes, because it has a lone pair right here. Okay, so it can. So if you look at the solubilities are going to be similar here. That's in water, will be similar for the two compounds. What's going to be really different is the boiling points, because the boiling points are affected with the fact that this has dipole-dipole, because it has a dipole interaction, but it also has hydrogen bond, or it does not have hydrogen bond. So the boiling point is 35 degrees. Okay, you look at the alcohol here, it can hydrogen bond with water, and it can hydrogen bond with itself, because it has an oxygen, and it also has a hydrogen. So look, its boiling point is 118 degrees. So what's the difference between 118 and 35? 83 degrees. So similar molecular mass, but the fact that butanol can hydrogen bond with itself causes its boiling point to be 83 degrees Celsius more. Okay, so which of the following pure compounds can form hydrogen bonds? Which can form hydrogen bonds with water? So when we're looking at these, the first one, okay, so does it have nitrogen, oxygen, or fluorine plus a hydrogen? If it has no hydrogen, but it has one of these three, then it can hydrogen bond with water. But it has to have all of these to hydrogen bond with itself. So can it form hydrogen bonds and then with water? So this can do both. This one can form hydrogen bonds with water because it has a nitrogen with lone pair, and then it can form hydrogen bond with itself because it has a hydrogen. Okay, the next one is triethylamine. Okay, it cannot. So this is no, but it can form hydrogen bonds with water because it has a lone pair. It has the nitrogen, the lone pair. The next one is 1, 2, 3, propanol, and it has oxygen with its lone pairs, and it also has a hydrogen. So this one's yes and yes. Okay, the next one is ether. 1, 2, 3, 1, 2, 3. We just looked at that. And it does have an oxygen with lone pairs, so it can form hydrogen bonds with water, but it cannot form hydrogen bonds with itself because there's no hydrogen. The next one is pentane, 1, 2, 3, 4, 5. This is an alkane, and it has no oxygen, nitrogen, or fluorine, so it is no on both accounts. The next one is an alkene, and it would also be no and a no. Okay, we have an oxygen here. If you draw the Lewis bond structure, you'd see that this is a acetone, and it's a ketone. So it has an oxygen, but it does not have a hydrogen. So no, it cannot hydrogen bond itself, but it can with water. So, and the next one is a carboxylic acid. And as you can see, it has the oxygen, lone pair, and it also has the hydrogen. So this is a yes and a yes. And the last one is an aldehyde. And you'll see that they're classified like the ketone above. This was a ketone. This is an aldehyde. Because that hydrogen is not connected to a heteroatom, that would mean no, but it can hydrogen bond with water because of its oxygen with layers. Okay, problem 4. Predict which compound in each pair will have a higher boiling point and explain your answer. Okay, so the first one is an ether, and versus an alcohol. Okay, the alcohol is going to have a higher one, and that's because of hydrogen bonding with itself. Okay, we're talking about boiling points here. All right, the next one here, 1, 2, 3, 4, 1, 2, 3, 4. These are the same compounds. So they're going to have the same. This one here is 5, 1, 2, 3, 4, 5. This is called pentane. Has carbon 5, or 1, 2, 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. This is 2-methyl butane, and this has C5. So they have the same molecular weight, but this one's going to be branched. And just so you know, we have a slide and it shows that if it's not branched, it's going to have the higher boiling point. So the non-branched. So let's go ahead, let's circle this one. Let's circle this one, the non-branch. And then the last one, 1, 2, 3, 4, 5, it's still pentane. Or 1, 2, 3, 4, 5, it is chloropentane. This has one, it has a dipole moment. Okay, so it has dipole interaction, and also has a higher molecular weight than pentane itself. So it would have the higher boiling point. Okay, problem 5. Circle the functional groups in the following structures and state which class or classes of compound the structure belongs to. Okay, so you need to get some index cards and start really learning your functional groups. This is an oxygen. Oxygen can be bonded to two things. It's bonded to a carbon and a carbon. So this makes it an ether. Okay, it can be bonded to two things. That's an ether. This is a double bond. That makes that an alkene. If you do the Lewis structure of a COOH, you will see that that is a carboxylic acid. Once again, we have an alkene here. If you do the CHO, you will do the Lewis bond structure and you'll see that that is an aldehyde. And that's a carbonyl. And so carbon, once again, can be bonded to four things if it's double bonded to the oxygen. And usually it's going to be bonded to the whatever the chain is. So what you're looking at is over here. If it's a hydrogen, it's an aldehyde. Here, once again, we have carbon to the chain. It has a carbonyl, but it's bonded to an OH. So these are all the same. The OH makes it a carboxylic acid. Okay, this one here, you have a carbon with a nitrogen. That's an amine. A-M-I-N-E, amine. This, when you have a six-membered ring that's alternating double bonds, this is called an aromatic. And we'll have a couple of chapters on aromatic systems in organic too. Okay, once again, you find your carbonyl here, and this carbon is connected to the ring. That's a CH3. That makes that a ketone. So when you have your carbonyl, when your carbon's connected to the rest, you look what's over here. If it's a CH3, then that's going to be a ketone. Here, you have the carbonyl once again. You have whatever the rest of the ring, whatever that carbon's connected to. But now you look and you see that it's connected to an OCH3. So if it had been an OH, it had been carboxylic acid. If it had been an H, it had been aldehyde. If it had been just a CH3, it had been ketone. But because it's an OCH3 with a carbonyl, it's called an ester. So this is an ester. Once again, we find the carbonyl here. That carbon is going to be connected to the rest. And so then you look what's over here on the other side. And when you see that it's connected to a nitrogen, that makes it an amide. An amide or an amide, either one's okay. You see how that's different than an amine? Okay. So the difference is that carbonyl. And then this is a alcohol. Alcohol.